I'm not going to have time to finish all the slides in this talk. There's way too much material. However, there's a link in the first slide here that already has the PDF available for you to download and study at your leisure. Some of you may even want to download it now because you'll then be able to click on some of the links that I won't have time to delve into and maybe even look at some of the code. I won't be showing you the code. I'll be talking about what it does, and then where you can find the underlying code is all in the links. But you can find your own copy of the slides right there. Okay, so this is about OpenSSL in the Postfix mail server. I'm the maintainer of its TLS stack, but originally much of the code that I'm talking about is of course written by Viktor, who is the primary maintainer of Postfix, but the TLS stack was originally implemented by Lutz Janneke, who is an early contributor to OpenSSL. He was actually one of the founding, developers in the OpenSSL project, along with some others. And he still even recently, contributed some code a few years back. I remember there were a few commits from Lutz. Anyway, so this has a long history. Okay. So I'm going to be showing you application areas to which Postfix puts OpenSSL, talking briefly about what they achieve. And I wanted to mention that the underlying code in Postfix is much easier to read than in many other cases. We comment the code heavily, explaining why we're doing things. The code is reasonably carefully written. It's VC style. And so you should be able to learn from it. It's going to be a better set of examples than some of the OpenSSL demos from which you might also learn how to use OpenSSL because it's production code, B, it's better commented, and it's actively maintained and used rather than just being demo code. So this is a good place to learn from, in my opinion. Anyway, so moving along, background. So what's interesting about SMTP in terms of TLS is that in SMTP, the user doesn't specify whether email is to be delivered encrypted or not in general. Right? You just send an email to an email address. The mail servers decide when and where to apply TLS opportunistically. So unlike when you use a type, say, URL into a browser, if they actually specify the HTTP or HTTPS part, they're explicitly opting in or out of security. With email, the mail servers decide, and what's more, the history is such that the default decision is, well, maybe you do TLS, maybe you don't, it doesn't much matter. You do best effort. And this makes the policy landscape much more complicated. So email deals with a lot more scenarios than you would find in the web. So SMTP is opportunistic, and you can read all about why and horrible details. But so you might think that TLS in email is always weak, but it's not always weak because there are two competing technologies for making email security actually robust. One of them is DANE, that I talked about yesterday. Some of you may have gone to my talk. The other is something called MTA STS, which was cobbled together by Google and Yahoo and a few others, mostly because they didn't want to or were unhappy with DNSSEC. So they wanted to put together a kludge that avoided dependence on DNSSEC. And it's weaker and it's harder to deploy, but it serves their needs. And so communications between some of the major players uses MTA STS rather than DANE. Although Microsoft is now deploying DANE, so we'll see what happens down the line. Okay, so even though we think of email as mostly in secure delivery protocol, if we actually look at the statistics of how much TLS happens in email, Gmail publishes a transparency report. There's a link to it up there. And in the Gmail transparency report, you see that roughly at the time of the Snowden report back here in 2013, 2014, about 30% of the email traffic was using TLS. We fast forward to 2025, and at least the outbound traffic is 98% encrypted from Gmail. So actually, it's higher than in the web, right? We were hearing figures of 80% of web traffic is encrypted. 98% of email traffic is encrypted. Opportunistic security works. I actually have an RFC about that, 7435, if anybody bothers to look. It's some encryption, some of the time, is better than none. So if we look at the Gmail inbound traffic, they report 100% is encrypted. Now, of course, it's rounding. It's 99.98 or whatever it is. But essentially, all of the email coming into Gmail is TLS encrypted. Perhaps because, in part, if it's not, Gmail might actually, put it in a spam folder. So people have learned that they'd better do TLS if they want to deliver mail to Gmail. So probably even the spammers are driving up this number, because especially they wanted to use TLS. But anyway, TLS is pervasive in email, even though it's optional. All right, brief history of Postfix. So Postfix was born in the late 90s after a long history of send-mail vulnerabilities. I was around for one of the first major ones, the Morris worm in '88. I actually had stayed awake all night fighting the thing on the systems that I was managing at the time. But anyway, Postfix was an alpha release to a very select group of people who Vitsi knew and trusted to help him improve the system in '98, public beta in '99, then 1.0 came out in February 2001, and I actually started using it a few months later. Vitsi merged TLS support into Postfix in 2005, but prior to that, Lutz actually contributed Postfix TLS support right after the beta, just a couple of months after the beta. With OpenSSL 092. I don't know how many of you remember that there was an OpenSSL 092. I certainly never used it. But at the time, he also contributed TLS support to SendMail and Postfix, and it eventually evolved into the code that I'll be talking about now. So there are, at this point, essentially 25 years of improving and evolving TLS support in a variety of application areas in email. So Postfix 3.11 is now 144,000 lines of code. You can compare that in terms of code size. OpenSSL is 450,000 lines of code. So Postfix is not that much smaller than OpenSSL, though it is not a library, it's a system. So in some ways, the complexity can be expected to be a little lower in terms of the complexity of maintenance. But Postfix has about 13,000 lines of code related to its SSL support. So some people are surprised by how much code that is. So you'll find lots and lots of things that work with OpenSSL inside it. It's, as you can see, almost 10% of the code base is TLS-related. Over its 25-year plus history, approximately 6 CVEs in Postfix, most of them minor. And some of them affecting multiple products. Vitsi discovered some protocol issues, and those became CVEs. But they affected other implementations as well. They weren't really Postfix problems as such. Okay, a little bit about Vitsi. So you can read these quotes. But basically, he's an unusually methodical programmer. Yesterday I heard in conversation somebody remembering, actually it was Peter Gutmann was telling me, that the way Vitsi reviews his code is he prints it out and reads the functions backwards from the bottom up, which really helps you sort of notice the important parts first and avoid glossing over the key details after you've read the initial bits. So he very carefully analyzes the code, and he makes very few mistakes. The code is rock solid. And the basic philosophy is backwards compatibility, and even as lots of snapshots of the software appear. Development versions, sort of the equivalent of OpenSSL on GitHub. Only Vitsi doesn't release his code through Git. He just releases a snapshot every few weeks or sometimes a month apart. Those snapshots are production quality. They may not be stable in terms of feature set, but he doesn't release code to people that is kind of lower quality. It's rock solid at every stage. Okay. So I've been working on Postfix, but I joined late, 2001. I missed a few years of the early development. But already sort of a year later, I ran the mail servers at Morgan Stanley that did the Google IPO, and Postfix worked very well for that, and has continued to work very well for many users since. I refactored the TLS stack after VC adopted in 2005 with the experience of running a large commercial mail plant, 80,000 users and so on. I could bring some insights that from an environment that the developer didn't have access to. So really, I had the privilege of seeing Postfix in action in a much larger scale than its primary developer, and so I contributed some features. Another sort of email developer, but actually a contributor to the Dane standard, reached out to me somehow, and maybe on the Postfix users list back in 2013, says, why doesn't Postfix do this Dane thing? And I'd never heard of it. But I read about the Dane specification that at that point was a year or two old, and said, hey, this makes sense. So I started implementing it in Postfix, and in the process, rewrote the Dane specification as an RFC for email. It was originally focused on the web, where it still hasn't taken off, but it's very appropriate for email. And then later, in 2016, just a couple of years down the line, I integrated Dane support in Postfix, in OpenSSL, and you heard about that yesterday to some degree. Okay. This is a picture of Postfix. It's actually an outdated view of the Postfix architecture. There are a lot more components now. So this is published on the postfix.org website or from some talk. But if I really were to flesh this out, there'd be a lot more parts. What I wanted to highlight here only is that the only components we're interested in is the SMTP server receiving incoming email from the internet entering Postfix. And then there's, on the other side, an SMTP client that sends email out to the internet. And there are all of these other helper processes. It's a very carefully designed system, which, unlike SendMail, is not a monolithic thing where any one component going wrong compromises the whole system. Postfix is designed as a bunch of libraries and lots of little microservices running inside, each one doing a dedicated task written to solve just that problem. And they all drop privileges and don't trust each other even. So the sensitive components decide what they're allowed or not allowed to do based on their own configuration and not on input from the other components. They can just pass message data to each other, but they don't tell each other what to do. They're not trusted to do that. Okay, so yeah, never mind. You can read about that separately. So TLS in Postfix. This is really the subject of the talk. As I mentioned, the server receives email. It's an MTA. It is also a submission agent. This is when you, as a user of Thunderbird or Mutt or whatever, send a message off, and Postfix receives it and then relays it to other domains from you. So it's an outbound message submission server. The TLS settings are not necessarily the same between the MTA that receives email from the outside may be willing to receive email in the clear. But the message submission agent that receives email from users wants to have them authenticate with usernames and passwords in many cases, don't want to send those in the clear, so the MSA will have a different set of TLS settings. So already we see some policy variation within the system. And Postfix can also even in server-to-server deployments. If you have an environment where you maybe have some servers in distant portions of the network that want to still send mail through your relay, but they're not inside, not on the inside, they're located at the edge of your network, they may essentially set up in a TLS VPN. The TLS may be mandatory between a client and a server, and the client may authenticate with a certificate. So Postfix supports that use case as well, and if you look in the code, you'll find how it does that, and I'll talk about that in a moment. All right. So one interesting thing about Postfix is because SMTP is different than the web, the kind of settings that especially distributions put in their shared OpenSSL.conf file are often not appropriate at all to an email server. Email servers need to do best effort TLS, not maximally strong TLS, and then not be able to communicate because the TLS encryption isn't strong enough. And often when you set the TLS settings too strong in the case of email, what happens is the TLS part aborts, and then you send the mail in the clear because you decided that the TLS connection was too weak. But surely in the clear, it's better. So Postfix initializes OpenSSL explicitly. It does not go with default initialization. So it calls many of these functions that you see listed there as relevant APIs, and by default doesn't load the configuration file at all. It runs with compile time defaults as adjusted by its own various settings. But the idea is not to be affected by various random crap that some distribution will put in a system-wide OpenSSL.conf that would be detrimental to delivering email. On the other hand, sometimes you actually want to leverage the capabilities of what would be in OpenSSL.conf explicitly to help the mail server initialize some feature of OpenSSL that Postfix doesn't directly have controls for built in, but that you can set via the configuration file. So I, on my system, have an OpenSSL configuration file that only Postfix loads. It's not the shared system-wide one. It's an alternative file in which I put OpenSSL settings, and then Postfix imports them. So you can find examples of how to do that in this code if you follow the links. I'm not going to show you the examples. You can do that when you download the talk for yourself. Then, having obtained an initialized SSL context, that per whatever's in that file, Postfix further tunes it with this function TLS server init, which contains lots and lots of tweaks to the SSL context, loading trusted certification authorities, and all of this stuff that you'll see in a moment. So this sets protocol options, trust options, verification callbacks, all of that. There has been import of ideas from Postfix back to OpenSSL. Originally, when I was writing this code, to select which protocols were supported, I had to use these SSL op, no, SSL v2, no, SSL v3, ugly Boolean options. But really, what you want to say is a protocol range. I want to support everything from this version of TLS to that version TLS. So the minimum, maximum protocol settings were something that I argued for back when I was developing code for Postfix, and it ended up in OpenSSL. But it was an idea that originated while trying to implement TLS in Postfix. Okay, so default security level 0 because we're SMTP and some encryption is better than none. Session caching is a bunch of the work that function does. And it also, because we want during the TLS protocol, we want to be able to find our own configuration in the middle of various callbacks. This is probably something that lots of applications do. You tag your SSL objects with some application-specific data. Sort of these functions, SSL get new index that allows you to reserve a slot in the SSL structure to which you can attach your own context so that in the middle of an SSL callback, you can find out your own settings and then react in the callback appropriately. So you'll find code that deals with that. Stateless resumption key rollover. I'll spend a bunch of slides talking about that. Postfix has support for raw public keys because in SMTP, certificates aren't always the appropriate way to authenticate a client or server. Sometimes the public key is good enough and, in fact, better. Postfix has a fairly sophisticated configuration for loading server certificate chains. You'll hear more about that. Okay, so loading certificate chains. First of all, CA file and CA path are by default not even loaded. So Postfix normally, as an SMTP client, because it's opportunistic TLS, it's unauthenticated, so we just need to complete a TLS handshake to guard against passive wiretaps. But if there's a man in the middle, they could have already man in the middle the DNS responses and sent us to the wrong server. So it hardly matters to authenticate the the connection with a certificate, so we don't need a CA file or CA path. But you can load them, if we're getting client certificates, then we almost never want to trust some third-party CA to tell us who our trusted clients are. You know them directly by pre-configuring the expected fingerprint of their client cert. Okay. The server's own certificate originally, OpenSSL had support for just RSA. DSA got added pretty early, so you might have had separate settings for here's my RSA certificate, here's my DSA certificate. Eventually, in OpenSSL kind of 0.9.9 and 1.0, support for EC appeared, and Postfix grew yet another configuration parameter. Here's my ECDSA certificate. But the game gets silly the more algorithms you add, and keeping inventing more application configuration parameters that users have to worry about, one for each new algorithm type is insane. So Postfix decided that we're going to have just a single parameter that's a list of chains. And we don't care which algorithms are in them. The algorithm will be determined by the content of the private key and certificates. So in Postfix, the way that a certificate chain is configured is that it's a key followed by a certificate followed by a list of issuers, and then you can have in the same file another key and another and entity certificate matching that key, and then even more issuers and so on. And such a sequence makes up a chain of chains. So Postfix supports this kind of enriched PEM file format in which one or more chains appear in the same file. Or they can be in separate files, but the order has to be the same. So it's key, certificate, issuers in any number of consecutive files. So there's a list of file names, and together they yield a list of chains. And this has worked well, especially because for SNI, we want to store these things indexed by the name of the server we're connecting to, and we want to store them in some sort of database as a blob. And so especially this notion of explicit separate parameters for each algorithm would have worked fairly poorly. So this code got added roughly at the same time that I finally implemented SNI support. So you'll find code for that. And what that code shows you is all of the low-level routines for parsing PEM files to extract out of them certificates and chains and so on. What's nice about this code is that it's atomic. It avoids race conditions. If you put your key and cert in the same file and do it right, then during key rollover, you're reading only either the file with the previous key insert or the file with the new key insert. You'll never read the key from one file that might be old and the cert from a new file that might be new and then be briefly misconfigured because you happen to start your server at exactly the wrong moment during key rollover. So Postfix avoids the race condition that you would normally see if you were configuring your key insert files separately. Of course, the person creating the file has to do it atomically, right? Create a new file on the side and then move into place when it's got the right data in it. Okay. So as I mentioned, SNI-specific chains leverage this capability of having the key insert and another key and another cert all as a blob that Postfix parses. The databases are used to store this stuff. And of course, you'll find the callbacks for handling SNI in Postfix. One of these days, somebody will rewrite the way that Postfix does SNI. Sorry, not Postfix, OpenSSL does SNI support. There's this notion of changing the SSL context associated with an SSL connection in the SNI callback so that it sees a context which has a different set of certificates. This is a little bit dated and isn't a good way of doing things. All right. SNI processing, yes. Lots of code to do with SNI processing. Client certificates, they're typically optional. There used to even be times when if you ask for an optional client certificate, some clients might think, oh, the server demands a client certificate. I don't have one. Let me break the TLS connection. So we don't ask for client certificates by default, but if you need them, you would typically only do this on the submission port, but not on the port 25, where you're taking incoming mail from strangers. So you limit the damage to just the place where you expect clients to need to authenticate. There's a capability to either ask for, but allow clients to not have client certificates, or LUTs had this feature to require client certificates. Unfortunately, that feature is made less useful than it could be, but for backwards compatibility reasons, we can't easily change it. It requires client certificates that are CA issued from a trusted CA. And that's not typically what you want. So this require cert feature is rarely used, but you can find code for that. And there are, of course, callbacks for processing the client certificate that the server receives. Postfix, unlike many other TLS users, does not terminate the TLS handshake when the authentication requirements aren't met. It always allows the handshake to proceed. The verification callback always says, life is good, keep going. And then if at the end of the handshake completion, we find that, yes, the handshake completed, we have an encrypted channel, but we're not happy with the peer's credentials, we do a graceful disconnect at the SMTP layer. The server might send the client, sorry, I'm hanging up on you, 421, go away, or 521, go away. And the client might send quit, sorry, I'm unhappy. But it avoids ugly logs about, that users get confused about with TLS connection failed and some cryptic message. No, the connections terminate gracefully. Yeah, so that's done a little bit differently. But if that's what one does, one has to be careful not to lose track as to whether the authentication actually completed or didn't. So that's checked post-handshake, and that's an important check not to forget to do. Session tickets. Session tickets got added in sort of TLS 1.1, 1.2 sort of timeframes. They worked even with TLS 1.0. They're an extension. They allow the server to offload its state to the client. Instead of needing to keep a large cache of all of the sessions the server has with every client, the server sends the client an encrypted blob that the client can return to the server when it reconnects. And then the server says, yes, I used to have a session with you. Thank you for handling the storage for me. And the way this works is that every session ticket, the server gets to generate a 16-byte name. You usually fill that with completely random data, so to avoid collisions. So this allows the server to know which encryption key the rest of this data got encrypted with. The server also sticks initialisation vector in the ticket to avoid, encrypting every client's data with the same IV. That would be bad. That would lead to various attacks if you were using the same key with the same IV. Then it's got the ticket. And then, importantly, Peter talked about encrypt and MAC. There's a message authentication code, also 32 bytes, allows you to use HMAC SHA-256, and that is a protected checksum over the whole ticket. So, by default, OpenSSL issues these tickets. It's standard action in TLS 1.2 and TLS 1.3, but the encryption key for encrypting and decrypting these tickets in OpenSSL is generated during initialization and then never changes by default. So as an application developer, you can implement callbacks to periodically roll these keys. But that takes code, and that code can be found in Postfix. So if you like the way that Postfix is doing it, you'll find the associated code. Postfix just has to remember two keys. The one that's currently creating new tickets and also decrypting them when they come back in short order. And the key that was the previous one that was decrypting tickets that you issued before the last over but that haven't expired yet. So it allows you to introduce a new key without immediately disrupting sessions that were encrypted by the previous key. So two keys are really enough to keep a sort of a sliding window of support for session tickets. So the active key encrypts and the previous key decrypts. Okay. There's a server callback that's optional that avoids the built-in never-changing key and allows you to take over the process of session ticket encryption. You don't actually do the encryption operation. What you're providing is a pre-initialized encryption context to OpenSSL that it's going to use. So you set up all the key material and then tell OpenSSL, here, you can encrypt with this. That's inside the function registered via that callback. What happened? Oh, yes, wrong button. I would like to, I've been talking about it for years. My credibility on this is kind of shrinking. But at some point, it would be nice to do something like that in OpenSSL. But the barrier to building this into OpenSSL is that one has to make some tricky decisions about how this interacts with threads. Postfix is single-threaded, so that kind of question doesn't come up. And also what kind of protocols and support for agents that might extend this not just from one machine, but across a cluster of nodes that all want to share session tickets because they're behind a load balancer. And so a session created on one machine might need to be resumable on another. And so you need to share the session ticket state across multiple nodes. I know that this, for example, somehow Google is able to make it work. When you send mail to their MTAs and you establish a session with one of them, you connect to another, and in fact, that session is still valid. So they've arranged to have the same key encrypting and decrypting session tickets across an entire data center cluster somehow. That's not available in OpenSSL. It would be nice to have that, TBD. Raw public keys. Raw public keys are an idea that allows you, instead of the server or a client returning a certificate to prove its identity after it signs some messages in the handshake or shortly before, to just return the public key and say, that's my credential. Now, of course, in order for that to be validatable, the client would have to know what public key to expect, or the server would have to know what public key to expect from the client. And sometimes that's exactly what you have. In the case of a client that you've prearranged to create a VPN with, a hardwired server-to-server connection, you would have that public key in a database on the server. And if the client presents it, you can look it up and say, aha, yes, that's one of the clients I trust. But also with Dane, Dane TLS records might give you enough information that make it possible to identify the expected key from a peer without having to need any certificates. So this works. The support for it in OpenSSL was added by Todd Short, who I think worked at Akamai for a while. I don't think he's there now. But he implemented it, and I helped him kind of tune it a little bit and integrate it with OpenSSL's Dane support. And Postfix uses this to negotiate raw public keys whenever it's appropriate. Whenever it doesn't need a certificate and a public key is sufficient, Postfix is happy enough to receive or send a public key instead. So you can find lots of code around RPKs, both client-to-server and server-to-client. Key exchange supported groups. Postfix TLS support was implemented in the day when RSA key exchange was common, and you had to have non-default settings for even getting Diffie-Hellman key agreement and any kind of forward secrecy. So initially, Postfix would have its own compiled-in Diffie-Hellman parameters that were default, and then a user could generate their own if they wanted to not be vulnerable in case that particular key got attacked by some really highly capable adversary who could do the pre-computation to attack Diffie-Hellman. Anyway, over time, OpenSSL started automatically figuring out what the right Diffie-Hellman parameters might be, or especially for EC curves, automatically negotiating a curve mutually supported by the client and server. And so Postfix has over time backed off from encouraging users to explicitly specify which curve to use or which Diffie-Hellman parameters to use, and gradually switched to auto-negotiation. But behind that, there's still, even though we're auto-negotiating, there was still the total list of curves among which the negotiation process would choose. And Postfix would, for a while, was setting that to a list of sensible curves or a list of sensible Diffie-Hellman parameters. Now, with the advent of MLChem and so on, the syntax got much more interesting, and it just didn't make sense in Postfix anymore to encourage users to do this. And so we're telling users, turn all of that stuff that we've been doing for 20 years off, let OpenSSL set these things. So there's now code to leverage OpenSSL's supported groups configuration. And if you don't like the OpenSSL default for some reason, if you need to override it, you can use that explicit initialization, load a file which specifies the supported groups using OpenSSL syntax, rather than have it be part of the Postfix config. I also mentioned that we hear every once in a while of servers where the larger client hello that results from sending MLChem key shares by default in OpenSSL causes some problems with some middle box. Usually it seems they fix it within weeks to months. So originally I got a report that Boeing.com you couldn't send mail to because their servers were choking on MLChem key shares. They're not choking on them anymore. There was another site that I was using for testing that had a similar problem. They fixed it. So maybe MLChem key shares are not so bad because the people who have trouble with them fix them in time for it to be not your problem but their problem, because I guess they encounter it not just with your sender but with lots of others and are so forced to fix it. PQC, I've already talked about it. Yeah. So Postfix no longer tries to mess with the supported groups. And of course, over time, there'll be more settings that OpenSSL might make that invent for which it doesn't really make sense to create application-specific controls. And so explicit initialization, setting the application name, setting the file to load, makes sense for an application that on the one hand wants to not by default have its behavior changed because some distro decided to mess with TLS. But if you want users to be able to take advantage of new features in OpenSSL that you didn't anticipate, instead of having to take every OpenSSL function and provide an application control for it, it makes sense to leverage the OpenSSL config file to allow users to take advantage of features that you didn't anticipate. Okay. Postfix has an external session cache. In that multi-process architecture, the SMTP server isn't a single multi-threaded process. It's lots of processes, one per connection, very traditional Unix-style client-server architecture in which there's one process per client. And it works okay for SMTP. SMTP usually, the message rates, the messages are large and connections are not that many. So 100 processes can handle a very large mail plant. It's not that we get tens of thousands of messages per second in email. Usually, even a large server will get hundreds of connections per second, not thousands. And a few processes can handle that just fine. So Postfix as an external session cache allows all of those separate processes to resume sessions that were started by some other process. So instead of storing sessions in memory, sessions are stored in a database managed by a server that mediates access to this cache. So you'll find lots of functions that deal with sharing the session cache and externalizing it, callbacks for creating a new sessions, for retrieving old sessions, and all of that. So that's all in Postfix. Okay. So we've talked about initialization. This is now server TLS connection setup, right? So once we've created our context and created all the various callbacks, the server actually might at some point accept a connection, get a start TLS command from a client, and now it's time to actually do the handshake. So Vitsi discovered a vulnerability in lots of applications that do start TLS. In other words, they start in the clear, and then some application command comes along and says, okay, no, let's now turn on TLS after we've talked for a while in the clear. And the problem is that if you have a buffered I/O stack, you might have received over the wire in that plain text connection more data than you've so far processed. So when you see that start TLS command, you've read it, but your buffering I/O layer may have read some additional commands after the start TLS verb. And you're not processing the start TLS verb, and you perform the TLS connection, and then you go back and now you start reading your newly TLS-enabled buffer, but the buffering layer lives above the TLS stack. And though you think you're now reading encrypted content, you may actually be reading content that was sent in the clear. Now, this issue isn't a Postfix issue specific, right? It applied to SendMail, it applied to many other products. And so Vitsi in debugging some stuff in Postfix found this in, 2000-something, 8, 9, I forget when it happened. So there was this multi-protocol vulnerability. It's one of the CVEs in Postfix, but it's really multi-application sort of application architecture issue. It's not really a protocol bug, but it's if you implement start TLS sloppily, you're vulnerable to this clear text injection attack. So anyway, so Postfix flushes any buffered data because it's the right thing to do before you switch to an encryption context, creates the SSL handle, configures ciphers. All of this stuff happens in the server start. You'll find lots and lots of code for initiating a connection, performing the initial handshake. Okay, TLS server start. So Postfix has this TLS bio function that deals with any TLS operation runs through this thing, and it both orchestrates handshake interactions with the SSL library and just read and write for data. And what it has to do to deal with primarily is dealing with non-blocking I/O. When you configure OpenSSL for non-blocking I/O, if the data can't be sent right away, OpenSSL will return these SSL error want read, SSL error want write kind of indications. So having to orchestrate the retries and figuring out whether the function worked or it didn't, and waiting for the socket to make the data available, all of that is handled by this TLS bio function. It's a good place to look at how that's done. One important detail that was actually a recent issue in a bunch of products, I forget, maybe it was something, it wasn't quite curl, but there was some product vaguely like that, where they forgot to clear the error stack before calling SSL read and SSL write. And the problem is that when these calls don't succeed, OpenSSL internally looks at its error stack to determine why the SSL operation didn't complete. And if you have left over uncleared errors from before your operation started, it can confuse the status that you get returned from SSL get error. So it's important actually before you call a handshake operation or before you call read and write that you've already dealt with all the previous errors and cleared with all the error stacks. It's a design defect in my view in the OpenSSL API really. We maybe can figure out how to fix that one day, but for the moment that's what we have to live with. That the error stack interferes with the reporting of what happened to this operation. The results from previous operations can interfere with getting a correct indication of the success of the current operation. The error stack has to be cleared. So all of that is in this code that you can go and look at. Post-handshake. Postfix is pretty careful to give the user a good indication of what happened during the handshake. So it logs the handshake properties, but it goes to great effort to report correctly the various negotiated parameters. So I've had to occasionally tweak that code over the years as OpenSSL has evolved to indicate the key exchange group correctly, the server signature correctly, whether raw public keys were used, whether the session is resumed, and so on. So all of the details of kind of the reflection, if you like, to look at what is the state of the connection can be found in the code that's linked on this slide. So it reports things like this anonymous connection from the DNS whitelist.org people, to my server. Key exchange was actually X25509 MLChem. So the DNSWL people are running a fairly recent version of OpenSSL and a recent version of Postfix that supports this. So cool, they're eating the same dog food that my server is. Okay. And of course, this also saves away in the application context the client and server names and so on, but only if they're authenticated. So in some cases, you're then able to make access control decisions based on the subject name of the client, but only if it's trustworthy. Okay. Just what's in the server? I only have 3 minutes left. I'm clearly not going to finish this talk. I'm not going to get to the client. So the server does explicit initialization, avoids web PKI trust anchors, right? Lots of fancy stuff about loading certificates, resumption keys, raw public keys, signature algorithms, non-blocking I/O, reflection. That's all the stuff we've talked about. Okay, what can I do in the last 3 minutes? So the client has lots of different security levels. It can be configured to not do TLS at all, ever, no matter what the server offers. It can configure opportunistic TLS. It can configure mandatory TLS, but without any authentication. Encrypt. Yeah, who cares who you're encrypting to? You may be talking to an attacker, but hey, it's encrypted. So the passive monitoring is not an issue, but everything else is. Fingerprint, you can specify. I'm connecting to a server. I'm also its manager. I know what certificate to expect there. Here's the fingerprint. Otherwise, the connection's invalid. It of course supports DANE since 2014. Supports dane-only, which requires the server to have DANE. DANE is an opportunistic level. If the server has DANE TLS parameters, you do DANE. If it doesn't, you do normal TLS. dane-only requires the server to have it. Otherwise, the connection doesn't proceed. And then this is secure, which is a web PKI authenticated TLS. So all of these various policies are supported with also additional parameter tweaks that can be looked up in the policy table. The global default for most domains is either may, or some sites enable DANE if they have a working DNSSEC infrastructure, and then they do DANE. Per destination policy. We also have a little bit of, I said earlier that the sender doesn't specify how a message is to be delivered with or without TLS. There is this new RFC called require TLS that allows the sender to optionally say, my mail is so important, it must be encrypted on every hop. So VC is currently implementing that. And it already supports require TLS no, which is kind of the opposite. If you would normally require TLS on this connection, allow some messages to opt out. Usually you want those for messages to the postmaster. Your TLS is broken. Here, please fix it. You want that to not require TLS for delivery. So anyway, there's that. Yes, the operator in our case is not the average naive user. A user of Postfix is presumed to have some technical skills. This is not, of course, always true, but they really shouldn't run their own mail server if they don't know anything. Use Gmail or something. But if you're running your own server, you should have some technical sophistication. So we provide them with a bunch of fairly advanced controls that they're expected to use sensibly. Right, so similar stuff to what I've already talked about in the server. You can find links to how the client initializes itself, and you can find how DANE policy is used, and I'm out of time. So probably we should do questions, if there's even time for any. Is there time for questions?
So in one slide, you were talking about the chains.
Yes.
Triplets chains, right? What we found with OpenSSL 3 is that loading the chains of the CA chains became quite slow. So the
trust anchors, not the server's own certificate chains.
Yes, but the trusted chains. So the traditional kind of suggestion is to go with the hashed symlinks in a directory and specify the directory. And now we keep finding, because Fedora changed it to use this default, a lot of software actually breaks because they don't expect a directory as a source for those.
All right.
In the Postfix case, when you specify these chains, do you anticipate issues with like performance issues?
So Postfix is not really affected by SSL performance. Mail messages take multiple hundreds of milliseconds or even seconds to arrive. The handshake is not a significant issue in email delivery. It's not like the web where you download a 1 pixel image over an SSL connection. You download it on average an 80 kilobyte message, and the message rate is much lower. But nevertheless, I can address your question. So first of all, the performance of parsing the CA file has significantly improved between OpenSSL 3.0, which was the first one with providers and the new encoders and decoders, to gradually in 3.2, 3.4, and ultimately 3.5. That stuff is now a lot better. It's not quite as fast as it was in 1.1 still, right, I believe. Right, we'd like to get there, but we're not quite there. But it's a hell of a lot better. So most sites don't notice the problem quite the same way anymore. However, at least in Postfix, I personally still tell people you don't need to preload all of these CAs from CA file. CA path really meets your needs in almost all cases. So certainly that's a way of avoiding loading 100 trust anchors when only ultimately one of them will be needed. A perfectly rational thing to do. It means you have to maintain a CA path properly. Not everybody has a well-maintained CA path directory, but if you're in a position to have it be properly maintained, then that's a good option. I should at some point improve the Siri hash utility that maintains it to be more atomic. Right now, when you're running Siri hash, any applications that are concurrently running might fail to verify a server because while the directory is being manipulated, some CAs may drop out of sight. This is an implementation defect that can be fixed and should be fixed. It hasn't become a priority for me, but maybe it should.
Yes. In Kerberos case, on PKIX, what we see is like 3 times slower performance even with the 3.2, 3.5.
3.5 is slower because it's doing MLChem,
No, this is not yet MLChem. This is normal.
Okay, well, all right. We can talk about that offline. I think I'm out of time, it seems.
Thank you.
Okay. So, yeah, please look at the code. Get in touch with me if any of it raises questions. But the idea is that the slides are really a take-home exercise. This talk is a teaser. The content is in the links behind the slides.